In this video, I'll talk about the moment of inertia of a system of particles with the individual particles. So we have 5 masses. The mass of each individual object is given, and the distance from the axis of rotation is also given, and we need to find out the moment of inertia of this system, and we also need to find out the rotational kinetic energy of the system. So first, let me tell you what the moment of inertia is. So in linear motion, we talk about the mass. The heavier the mass is, more force is required to move it, or more force is required to stop it if it is already moving down. The heavier the mass is, the more inertia it does have. So if you have a heavier mass, then in order to move this mass, you need more force. Or for a heavier mass, if it is moving, more force is required to slow it down or to stop it. But in rotational dynamics, the mass is now replaced by called the moment of inertia. And the moment of inertia depends on the mass, but it also depends upon the distribution of the masses, how the masses are distributed. Let's say, for example, here we have 5 masses. If these 5 masses are distributed much more further, then its moment of inertia would increase. That means, let's say it is rotating and you have more masses here, then you would require more torque or more energy to stop it. Okay, so watch my other videos about the mass and the moment of inertia and you'll get a clear understanding of it is. So here, just before I solve the problem, I gave you a little bit understanding or the concept which talks about the differences between mass and the moment of inertia. So whenever we solve the rotational motion, we'll talk about the moment of inertia. And in linear motion, we talk about the masses. So how do we calculate the moment of inertia? As I mentioned, the moment of inertia depends upon the distribution of masses. The more it is away from the mass or from the axis of rotation, the more moment of inertia it will have. The moment of inertia also means is the more torque is required to make this object spin or rotate about axis. So how do you calculate? This is the formula for calculating the moment of inertia. I stands for the moment of inertia, which is now the summation of mi or I square. And as we have 5 individual particles, I can simply write down m1 r1 square plus m2 r2 square, m3 r3 square, and so on till we get to the 5th one. The mass, this mass is 1 kilogram, so we have 1 kilogram. And the distance, you can put down the negative sign, but the negative sign doesn't matter here because it is the simply distance or it is a square, so the negative sign won't make any difference. And this distance is 20 centimeter, so we need to change the 20 centimeter to meter. It will be 0.2 meter, so that's what it is, r1 squared. Now for this mass, m2 is 5 kilogram and r2 is 10 centimeter, which is 0.1. This mass m3 is 10, and what is the r3? The position is 0, so the 0 square. M4 is again 2 and 10 centimeter, which is 0.1. M5 is 15 and 0.2 squared. And if you solve it, what you get is 0.71 and kg meter square. All right, so the unit is kg meter square, kilogram meter square. This is the mass and this is the meter square or square meter, kilogram meter square. And now let's calculate the kinetic energy, rotational kinetic energy. So in linear motion, the kinetic energy is given by half mv square, but in rotational dynamics, the mass is replaced by the moment of inertia I, and v is replaced by the angular speed omega, and we have half term here. So this is the rotational kinetic energy, half I omega squared, exactly the same as this one. You have to replace mass by I and v by omega. And when you know all the terms now, I is 0.71 and omega is 12.56. If you solve it, that's what you get, 6.1 joule. And as you can see, if this mass is further and further, then it will have more energy if it is in motion, or if it is not in motion, then more energy is required to move at a certain angular speed. All right, that's what the moment of inertia is, or it is an equivalent of mass in linear motion, or if you're talking about the rotational motion, then mass and the moment of inertia are exactly the same thing. Mass for linear motion and moment of inertia for rotational motion. So this is it from this video. I hope you like this video, and if you have any questions, write down your questions in the comment section below, and do not forget to like, share and subscribe the channel.